So it's my great pleasure to be here to help lead off after this some nice remarks from Pascal. The discussion about some of the topic areas and how we look to topic areas, how we learn from the past and look towards the future. My name is Jake Taylor. I'm at the White House Office of Science and Technology Policy, housed in that building that you can see there, adjacent to 1600 Pennsylvania. And I wanted to talk to you a little bit about a topical area. One of the working groups will be discussing this in more detail tomorrow, where we're learning about this boundary between science and technology and its impact upon society, and trying to draw from it some of the lessons that this Moonshot program here in Japan is really pushing towards, and then see what we can gain from that knowledge. So I work in a field called quantum information science, which tries to understand how the very limits that nature sets for what we can do with information can be reached. How do we realize the dream of being limited only by the universe and not by ourselves? One area that we've been doing this in for now more than 50 years, topical to the Moonshot, right, because that was 50 years ago, is in sensing, in the measurement of things. And this has led to transformations in our society. But I want you to take a lesson away, which is that there is a scientific path. That scientific path was the advent of the atomic clock in 1947. The first one based in ammonium at my home institution, the National Institute of Standards and Technology in Gaithersburg, Maryland. This enabled accurate timekeeping. This was then added on, it's the laws of quantum mechanics saying that you can make these types of clocks. This was added on to satellite missions, to microwave electronics and amplifiers, to initial cell phone technology to create, in the 1970s, the global positioning system. And I tell you this because you start with a science path, these different sort of pure science things. How do I make a great microwave amplifier? How do I make an atomic clock? You combine them together into an initial technology, which is a real distributed and deployed system, distributing where you are via clocks. But then it's hard to predict the future from that point. So you got to that initial value of some moonshot concept. And then what? Can you predict that taxi markets would be upended in the 2000s? Because you combine this with the internet, you get ride-sharing and ride-hailing platforms like Uber and Lyft and such. It's hard to know. You do know, though, that when you make these scientific advances that improve what you can do technologically, your society will be transformed. If you are able to do that research, if you're able to have the technical know-how and industry domestically, you can benefit, and your citizens can benefit from that. Some of the things that are happening more recently in this space are in new modalities of measurement where we could measure nothing like it before. And I think this is, for me, illustrated by the LIGO, the Laser-Based Gravitational Observatory, which observed the first in-spiral of black holes and the first gravitational waves, the fact that Einstein's theory of general relativity causes ripples. That wouldn't have been impossible if we had been constrained to what you might call classical sensors from the 19th century. But I think a lot of you are much more excited about the more challenging and transformative area, which is not how we measure things, but how we take the information that we bring in and compute with it. And this is the field of quantum computing. Some of the power of quantum computers is actually easy to understand, and it has to do with the fact that nature is quantum mechanical. Chemistry, materials, they behave according to quantum mechanics. And if we can understand those systems better, we can do better agriculture. We can create better cars. do better batteries, perhaps solve key challenges for an aging society, or a society beset with climate and other challenges. The underlying problem, though, is that the quantum mechanics problem space is extremely hard computationally. And we already knew of another problem like that, which is fluid dynamics, how a liquid or a gas behaves. And the solution that we have developed iteratively over 100 years is to mix computational techniques with experiments, analog simulations of your system. So that is, of course, what you call a wind tunnel, this object here shown with the car, to be tested for its aerodynamic properties, and then complemented by computational capability. So we already have, in the last 10 years, dramatic improvements in our ability to simulate another problem, which is the Schrodinger equation, which is changing how we understand materials, and will change chemistry over the course of the next 10 years. But the future in this space is really into the programmable quantum computing space. And programmable quantum computers are still some ways off. We've had some great progress in the last few years, but you should be aware that getting these systems to behave nicely is a challenge at the very limits of what humanity can do. So when we talk about moonshots, we want to talk about challenging projects. Getting nature to behave quantum mechanically in large scales is one of the most challenging things we have ahead of us. But what can you do with it? And not only that, but once you've achieved small-scale quantum computers, let us not stop there, right? Let us also remember that computers were very interesting, but computers networked together has changed the global economy. And it is hard to know how that networking technology, what impact it will have going forward. You can see in here, by the way, that there are moonshot-style opportunities in this particular field, but you have to choose how you're going to focus your effort. One of the things that I particularly like about this field is that we actually have mathematical proof of certain aspects of the problem space, which if you can achieve them are real home runs. So I'm going to use a baseball analogy. So this is somewhat convenient because many in the audience here appreciate, or have at least been exposed to baseball. I was at a group with the European Union diplomats, and in the European Union this is a less popular sport. But so in this area, you've got these home runs of factoring, which changes how we do cybersecurity, linear algorithms, and quantum simulation. And we're doing things down here right now, which you might think as hitting singles. So what's interesting is that it's not just that you want to get to this point out here, which is a 20-year prospect or longer, but actually along the way, we're very hopeful that there's a whole bunch of new applications to arise. So when you're doing these types of moonshot efforts, you should be aware that you want that long-term goal, but along the way, you'd love the promise of new discoveries. You don't have to know what they are. You just have to know that there's a fecund ground, a fertile space for finding them. And so this is more, by the way, from the government perspective than, say, from a private venture perspective. But it is critical that you identify the opportunity space to be broad, even if you don't know the answers. And I do want to bring up that point about not knowing the answers, because when we talk about a Apollo-style program, that is a known scientific challenge. You already knew that you can make a rocket, that you can confine air and protect people from radiation to the point that they could survive a voyage. It is a technological problem to get them to the moon and back. Whereas if it is a scientific moonshot, the whole point is you don't know the answer. That's what science is. You're asking great questions, and this came up in the earlier sessions. You're asking great questions, but you don't know the answer. And I'm very excited to hear about the prospects for organizing Moonshot around answering and asking good questions rather than developing specific outcomes. That being said, you want to find the paths along the way. You want to be able to, every year, come back and say, oh, I learned something new. If you don't learn, you're doing it wrong. Within the United States, in this particular field, we have embarked upon a grand effort to improve our understanding of the science behind quantum information systems. This is not a technology development effort. This is not something that would fall within the Moonshot rubric entirely. But it is a recognition that even though we see initial commercial applications, there is so much unknown science to be done that it is critical for the government to get directly engaged in improving our research in that space. Right, so this comes back to the question, how do you balance the partnerships between the private sector, academics and nonprofits, and the government? Because it is, if you're investing people's money, it has to be for a purpose that cannot be achieved by other means. And so one of the areas that we see this is critical in was when you're trying to do basic science, which is pre-competitive. It's before you have all of your knowledge in place, before you can make the business case to the capital markets that there is a market there in 20 years, or even 10. The National Quantum Initiative Act, which was passed just under a year ago and signed by the President, calls for an 11-year sustained effort in this space. We're just about 1 year in. The first year is to get everything stood up. I'm very excited that we've actually had a lot of progress in that space. Dr. Chris Fall was executing for the DOE portion of that, but we also have the National Science Foundation, and Rebecca Kaiser, who's here from there, we'll talk about that a little bit later, and the National Institute of Standards and Technology, which is actually a critical third part here. Is a science project, a science effort, but we also need to incorporate standardization, regulation, make certain that we're doing those things correctly. And this came up also in the earlier session. I'm very glad to hear that there's intersections to the policies around the science. And we also need to figure out ways to integrate the supply chain to enable the new science that's going to happen. And that's through, in this case, the use of gathering industry together into pre-competitive spaces, which is in the US something we call a consortium. And then finally, we have to coordinate it. And this coordination is done through committees. Who here has sat on a committee? Has anyone here sat on a committee before? Please, like, just raise your hand. Okay, I think more of you have sat on committees than that. It is a common thread. And as you know, the challenge in committee-based coordination is exactly counter to what Moonshot's trying to do, right? Because a committee is designed to take the most consensus-oriented pathway. So how do we actually try and do this broad scope program with committee work, but then make certain we do daring science, right? That is a real challenge. And a big part of it comes back to making good choices in our policy space. So in quantum information science, I wanted to show you this list because this is not unique to quantum information science. This is, however, specific to the challenges we run into right now when you're at that boundary between science and technology in relatively smaller fields. You need to figure out what the big challenges are, focus efforts on them, provide good metrics to the previous speaker's points. You need the workforce. You need a full cycle workforce. You need to show there are great jobs available in the future, that if you're in middle school, that you can be excited about quantum computing or quantum circuits or quantum sensors. In high school, that you can start to get your hands dirty with it and learn about it. That when you're taking your exams, you're engaging with it. People building a quantum computer and the companies that are going to do this are not just going to be physicists or computer scientists. They're also going to be marketers, machinists, and business folks who are trying to make the case, yes, I can sell this product. You need to get some awareness throughout that workforce space, and that means you need inspiration. At the top, at the bottom, everywhere in between. That's how you get that diverse workforce, a key point of the previous discussion. You need that industrial engagement, you need the infrastructure. You have to balance the disruption that it produces with the benefits it creates. This is this balancing of sort of security and other things with the growth that you can generate. And then finally, it's a science space. You need that international cooperation and collaboration. You want a big marketplace down the road, you have to build a community around it now and maintain that community. The other thing in the workforce space, I just want to be really clear about this. You know, we've been digging in on this a lot at the Office of Science and Technology Policy. You need to get that respectful work environment. We have a committee, the Joint Committee on the Research Environment, or JCOR, which is digging in on how do you get that inclusive background, how do you get the diversity in there, how do you maintain respect and provide a good research environment, how do you have that open approach to the research, how do you balance closed data and open data? Everyone's wrestling with it, as are we. And finally, how do you connect what you're doing to society? This is what makes it Moonshot, right? So I just want to end by saying that we're doing all this work right now, we're doing a lot of science, but the frontier really is going to be an industrial frontier. It's just we don't know what that frontier is. What's really intriguing, though, is that in this particular space, we have large multinational companies investing basic R&D dollars and doing science with it. And I don't know where that is going in this particular world. I don't know how these industrial partnerships are going to move forward, but I do know that the landscape continues to change. And as you develop these new R&D efforts and new programs, I encourage you to figure that out again, to look again. Hey, how do we work with these incredible companies? I know Japan has many great companies doing good R&D. How do you engage them again? How do you bring them back to the table? And how do you bring the other multinationals and other know-how from around the world in to make the great success you can? That's all I really wanted to say. Thank you so much for your time.